Functions and relations are central concepts in all of mathematics, and so we want to take a look at that now. We're going to start with the notion of relation, and then we'll see that a function is a special kind of relation. So starting there, a relation is simply a collection of pairs, x comma y, where x and y can be anything. They can be numbers, which is how we usually deal with them, but they could be people, they could be times of day, they could be all sorts of things. And a relation is a collection of these pairs where we say that if x, y belongs to the collection, we say that x is related to y. Now, this is a very broad type of concept, and it's deliberately vague so that the relation idea can describe all sorts of relationships between objects or people or numbers. So we're going to look at a few examples of relations and then define some terms involving them, and then move on to what makes a relation a function. So let's start with a purely abstract relation. We could let R be the relation 2 comma 3, 3 comma negative 1, 4 comma negative 1, and then 4 comma 3. So this is a relation containing only 4 pairs. So in this relation, there are only 4 sets of 4 pairs of objects that are related to each other. So under this relation, 2 is related to 2 is related to 3, 3 is related to negative 1, 4 is related to negative 1, and 4 is related to 3. So this is an example of a relation. Now, especially when our relations are fairly small like this, with only a few terms inside, we have a graphical way of describing this relation, which is often helpful. What we can do is we can list out on in one column over here all of the first elements of pairs in the relation, and then over here on the right we can talk about the second elements in pairs in the relation. So I can look at all of the different numbers that appear as the first coordinate of one of these pairs. And I see that 2 appears, 3 appears, and 4 appears. And then 4 appears again, but we've already written that down, so we won't do that again. And then for our second elements, we see that 3 appears as a second element in our pairs. Negative 1 appears as a second element in our pairs. And that's it. Those are the only 2 numbers that appear in the second spot of our pairs that are in the relation R. Now, we'll make this precise in a second, but we give these 2 sets of numbers or of elements names. The set of all first elements of the relation is going to be called the domain of the relation. The set of all second elements of the relation are called the range. And if we list all the elements of the domain in a column on the left and all the elements of the range in a column on the right, then we can use lines to indicate the relations between them. So we have that 2 is related to 3, we have that 3 is related to negative 1, 4 is related to negative 1, and 4 is related to 3. So we could describe this relation using this diagram here. And when we're dealing with small relations, that's often a simple way of understanding what it is. So let's define domain and range precisely, and then work out the domain and range for another relation that is not quite as small, where we're going to have to think about it a little bit more. The domain of a relation is the set of all first elements of pairs in the relation. The range of a relation is the set of all second elements of pairs in the relation. So when, as in the previous example, the pairs are just listed out in sequence, then you can work out the domain and range just by working through all of the pairs and writing down the numbers that you get, not writing down any repeats. However, for more complicated relations, or just larger relations, we're going to have to do things a little bit differently. So let's consider the following relation, which I'll call S. And S is going to be the set of all pairs P and T, where P is a person and T is a TV show that P likes. So this is going to be a much, much larger relation, because every time you have a pairing of a person with a television show that they like, that pair will appear in the relation S. So, for instance, the pair William Taylor, that is myself, comma, Doctor Who, belongs to S. And how do we know this? Well, because I happen to like the television show Doctor Who. And so that means that the pair PT, where P is me, William Taylor, and T is Doctor Who, satisfies the conditions for being in the relation S, because the first element is a person who likes the second element, which is a TV show. However, if you replace this Doctor Who television show with a show that I don't like, and I won't name anything so as not to offend anyone, but if you replace that with any television show that I don't like, then you would get a pair that is not in S. And similarly, if you replaced William Taylor here with any person who doesn't like Doctor Who, that pair would also not be in S. So this S here is going to be very, very large, because there are lots of people and there are lots of television shows and lots of ways of matching up a person with a television show that they like. So let's think precisely about what the domain and the range of this relation S are. So the domain of S is going to be a set of people. Now, we know this already because the domain has to be made up of the first elements of the pairs in S. And the first elements of pairs in S are all people. So we might be tempted at this point to say that, well, the domain of S is just the set of all people. But that's not the case, because remember that the domain only contains the pairs that only contains first elements of pairs that actually exist in S. So if there happens to be a person who doesn't show up as the first element of any pair in S, then they're not in the domain of S. And so when will a person show up as the first element of some pair in S? When will a person be related to a television show in S? That will happen exactly when that person has at least one television show that they like. And that's not necessarily going to be all people. Now, it might, we don't know, but we can't just assume that it's all people. We need to be more precise. The domain of S is the set of all P, where P is a person who likes some television show. If there's some television show a person likes, then the pair of that person with that television show will belong to S, and therefore that person will be part of the domain of S. But if there is no television show that person likes, then that person does not appear in any of the pairs of S. Now the range of S, we'll think about similarly. The range of S consists of television shows, but not necessarily every television show. In order for a television show to exist as a second element of some pair in S, there has to be some person who likes it, so that the pair of the person with the show appears as a pair in S. So the range of S is going to be the set of all T, where T is a TV show that someone likes. So we can see that the domain and the range of S can be slightly more complicated to describe than simply the set of all people or the set of all television shows. We need to think carefully about what the relation is that we're describing before being able to describe the domain and the range of S. We could come up with lots of other examples of this type. One good additional example for you to think about would be the relation of X to Y, where X and Y are people, and X is a parent of Y. And so that will mean that the domain of that relation would be the set of all people who are parents of some person, whereas the range would be the set of all people who have parents. And so there are situations where a relation might encompass every possible thing that it could for the range, but not necessarily for the domain, and vice versa. So we need to think carefully about these sorts of things. All right, now while S has many pairs in it, it's still going to have a finite number of pairs because there's only finitely many people, there are only finitely many television shows, so there's only finitely many pairs P, T that could exist. Most of the time in mathematics, we are looking at relations that actually involve infinitely many different pairs because we're usually working with real numbers. So let's look at an example of that. And here I'm going to let my relation be denoted by little f, which we'll see the reason for in a little bit. And I want to let f be the set of all x and y such that y is equal to x squared plus 1 and x is a real number. So this is a relation that we say is defined by an equation. This is defined by the equation y equals x squared plus 1. And given any equation with two variables in it, where we've identified one as the first component of the pairs and one as the second component of the pairs, we can come up with a relation that consists of all pairs of numbers that satisfy that equation, that make that equation true. So let's see some examples. The pair 1, 2 is in F. And how do we know it's in F? Well, it's because if we plug these numbers, 1 and 2, into the equation, x going in, or 1 going in for x, because that's the first entry, 2 going in for y, the second entry, we get 2 equals 1 squared plus 1, which is true. But on the other hand, if we look at the pair 3, 5, this is not in F because the equation 5 equals 3 squared plus 1 is false. So this relation contains a collection of pairs. Some of them, and for any pair, it either belongs to the function or it doesn't. It belongs to the function if, when you plug in those numbers for x and y, you get a true statement, and it doesn't if you get a false statement. Now, one really good thing about being defined by an equation is that it's very easy to check whether a pair belongs to that relation or not. You simply have to plug those numbers into the equation and see whether you get a true statement or not. Excuse me. So this relation is an example of the type of relation we're going to call a function. And the reason for that is the following. Because we've got a relation defined by an equation, and the equation is of this form, y equals something involving x, we have the following fact. For every x, there is exactly one y such that x, y is in F. And the reason for that is because once I choose an x, then the only y that will make the pair x, y lie in F is the y value of x squared plus 1. The pair x, y only belongs to this relation F if y equals x squared plus 1. And so, for example, we saw that 3, 5 is not in F. But if we take this equation, if x is equal to 3, then if we plug that x into the equation that we got, get y equals 3 squared plus 1 equals 10, this means that 3, 10 is in F. And in particular, there's no other number you could put in there in place of the 10 in order to get a pair that is in F. Now, intuitively, what this means for the relation F is that if you know the first entry, you can exactly predict the second one for a pair that belongs to the relation. Every first entry, which we're going to start calling the input, has only one second entry or output that goes along with it. There are lots of situations in real life where we want to have relations that have this property. So for instance, if you're running a department store, you want to make sure that every barcode on every item there gets matched up with exactly one price. You don't want the same barcode to ring up for two different prices at two different registers. The relation that takes a barcode as the input and the price as the output needs to be a function. It needs to only have one output for every input that can go into it. And there are lots of other examples that we have like this. If I take a look at the relation where I relate a senator, the United States senator, to the state that he or she represents, that's a function because every senator can represent at most one state, or can represent one state. And the relation of, say, a person to their mother is going to be, to their biological mother is going to be a function because each person has only one biological mother, and so forth and so on. There are lots of examples in real life and in mathematics where functions, that is relations where each input has only one output, are completely vital to understanding what's going on. So, let's define this precisely. A relation, and again I'll use little f here. A relation f is a function if for every x in the domain of f, there is exactly one y in the range of f, such that x comma y is in f. Now, when we're dealing with functions, we've got some notation that we use specifically for the inputs and the outputs to the function in that case. In this case, we write f of x for y. So this expression right here, it's pronounced f of x. And so what this means is that we can write down the relation f as the set of all pairs x comma f of x, where x is in the domain of f. F of x is just the second entry that goes along with the first entry of x in the relation f. And when we're looking at a function, there's only one element that does this. So in our example, we have that f of 1 is equal to 2. And that's since the pair 1 comma 2 is in f. And this is using the f that we had before. We have that f of 3 is equal to 10. And again, this is since 3 comma 10 is in f. And then f of 3 is not equal to 5, since 3 comma 5 is not in f. So this function notation that we describe here is simply a shorter way of describing the inputs and the outputs to a function. So a function takes a collection of inputs and to every input assigns exactly one output. So these are important. Most of the functions that we're going to be dealing with in algebra are going to be relations defined by equations. Now, unfortunately, it's not the case that every equation defines a function. Every equation with two variables in it defines a relation, but not necessarily a function. So let's see some examples there. Let's let little g be the relation defined by y squared equals 2x. So in other words, G is the set of all pairs x comma y where y squared equals 2x. And for the moment, I'll suppress writing down that we're only looking at real numbers for our x's and y's. This relation here, as it turns out, is not a function. G is not a function. Now, the only way, really, to show that a relation is not a function is to show that you have two separate pairs that belong to the relation that have the same first entry, the same input, but different outputs, different second entries. So if we want to prove this, we need to find a single x value that has two different y values that are associated to it. So in this case, we can just play around a bit and find some, but we'll see in a second how we can do things in a somewhat more systematic manner. So first of all, notice that the pair 2, 2 is in G, since if we plug 2 in for y and 2 in for x, we get a true statement. But also we have that 2, -2 is in G. And this is since -2 squared is also equal to 2 times 2. So this means that G is not a function, because there's a single input, 2, that has two separate outputs in the relation G. Now, the relation G is still a perfectly good relation. It's just not what we're going to call a function. So, there we go. Now, how might we have figured this out without just, say, trying some of these things or having a few pairs to test given down from above? One of the best ways of determining whether or not an equation defines a relation is solving for the output variable. So, to determine, sorry, let me get a new page. To determine whether an equation defines a function, you can try solving for the output variable. So for example, if we look at the equation that we had before, y squared equals 2x. So here we have determined that y is the output variable. That's sort of our standard. Although it is arbitrary, it's possible to think of these things with y being the input and x being the output variable, but that's rather confusing, so usually we're not going to do that. So for us, almost always, when we use x and y, x is going to be the input and y is going to be the output. So if x is the input variable, y is the output variable, we want to try solving for the output variable. So we want to get y by itself. We want to get y equals something, and we're almost there. We've got y squared equals 2x. In order to solve for y, we'd want to basically take the square root of both sides. gives us the square root of 2x. However, we remember that when we introduce a square root, we need to include a plus or minus. Excuse me. And this is precisely where the key is. So we get that y is equal to the square root of 2x, or y is equal to minus the square root of 2x. And this means that as long as the square root of 2x is not 0, y has two separate outputs that it could have for a given x. So we've got two outputs for the same x. So this means that g is not a function. All right, let's do another example. And at the same time, let's look at our more efficient way of describing a relation using an equation. So, I'm sorry, I'm getting slightly ahead of myself. We want to ask the following question here. Does the equation 3x plus 16 equal 2y minus 9 define y as a function of x? So this expression right here, y as a function of x, means that we are using x as the input. A function of blank, a function of variable, means that that variable is being considered the input. And whatever the other variable is considered the output. X is also sometimes called the independent variable and y the dependent variable. Because usually when we construct these functions in real life, we treat x as the again, sort of the input to the system, the quantity that doesn't depend on anything else that we're considering. And then y is the quantity that is supposed to depend on x. So x might be the time of day, y is the temperature. And we think that, oh, well, the temperature outside depends on the time of day. And so that's where this sort of notation comes from, or terminology, I should say. So to say that we want to define y as a function of x means we want to get y to be uniquely determined by x. So for a given x, we should be able to figure out what y is. So to solve this, we will take our equation 3x plus 16 equals 2y minus 9 and try solving for y. Using all the techniques that we have. So we get 3x plus 25 is equal to 2y. And then we want to get y by itself, so we'll divide both sides by 2. And we'll get that y is equal to 3x plus 25 over 2. And at this point, we're done, because we were able to solve for y. Now, for any given x, there is one and only one y that makes this equation true. So, since we were able to solve for y, in terms of x, exactly, without any pluses or minuses or anything else, this means that y is a function of x. So for example, if h is the function defined by this equation, Then, if we want to know what h of 1 is, we want to know what the y value is that has an x value of 1. Well, if x is 1, then y, the output, is 3 times 1 plus 25 over 2. That's the equation that we just got. We've got y is equal to this whole expression in terms of x. So that gives us 28 over 2 is 14. So h of 1 is 14, or in other words, the pair 1, 14 is in h, is in the relation h. Now, if we just wanted to define h, one of the ways that we could have done that to begin with would be to do it in this way, to define the relation or the function using this formula. H of x is equal to 3x plus 25 over 2. And this is a shorthand for saying that the relation h is defined by the equation where the output, remember h of x, this notation is always the output of the function, is equal to the expression over on the right, 3x plus 25 over 2. Let's make that definition more precise. The expression f of x equals capital A here, where A is an algebraic expression involving only the variable x, that is, no other variables, means that f is the relation of all x's and y's where y is equal to a. So it's telling us what the output is for the function given the input x. So for example, if f of x is equal to x squared minus 3x plus 1, then if I want to know what f of 1 is, I get that by plugging 1 in to the formula that I had before in place of every x. So in the original expression, we have f of x is equal to this whole thing, which means that if I want to know what the output is for an input of 1, I take that 1 and plug it into the formula or the expression x squared minus 3x plus 1 for all the x's. So f of 1 in this case will be 1 minus 3 plus 1, which gives me negative 1. So that means that f of 1 is negative 1. For an input of 1, the output of this function is negative 1. F of negative 3 is negative 3 squared minus 3 times negative 3 plus 1. Be very careful when you are evaluating a function like this, and especially when you're plugging in negative numbers, but really all the time, you should be putting parentheses around the numbers that you're plugging in, even if there weren't parentheses in the original expression. Basically, every time you are replacing a variable with some other number or expression, you should be putting parentheses around them. So negative 3 squared is 9. Negative 3 times negative 3 is also 9 plus 1. So we get 19. So that means f of negative 3 is 19. You plug negative 3 into this function, you get 19 out of it. Now, one thing that we need to be careful about is what happens if I ask for something like, what's f of a plus 1? Now, plugging expressions into functions turns out to be very important in lots of contexts, not only in algebra, but in calculus, in trigonometry, in all sorts of settings. And so we want to make sure that we understand this. When you are evaluating a function, as here, whatever is inside the parentheses behaves as the input to the function, which means that it is going to take the place of x everywhere x was in the original expression. So this, whatever is inside here, replaces x in the original. So that means that every time we see x in the original expression, we're going to replace it with a plus 1 in parentheses. So f of a plus 1 gives us a plus 1 squared minus 3 times a plus 1 plus 1. Now in this case, when we go and expand this all out and combine it together, we're not going to get a single number out of it. But that's okay, because our input wasn't a single number. What we are getting is an expression that will always be the output when the input expression is a plus 1. So if we expand all this out, we get a squared plus 2a plus 1 minus 3a minus 3 plus 1. And combining all this together, we get a squared, 2a minus 3a is minus a. Then we get 1 minus 3 plus 1 is minus 1. So in this case, we say that f of a plus 1 is a squared minus a minus 1. So sometimes you're working with functions and your inputs and your outputs are expressions rather than numbers. That's okay. Let's come back and look at a couple more examples of using equations to define functions, or trying to. So let's say does the equation y squared plus 8y plus 12 define equals x, define y as a function of x. So we've got that y squared plus 8y plus 12 equals x is our equation. We want to try to solve it for y. Now this one's a little bit more complicated. We need to work a little bit harder at it. We see that we've got an expression that is of degree 2 in y's. We've got a quadratic expression in the y's on the left. And to solve that, we're going to either factor or use the quadratic formula, which means that we need to get 0 on one side. So we get y squared plus 8y plus 12 minus x equals 0. And we want to try to solve for y. Now factoring this is unfortunately not really going to be feasible because the 12 minus x term over here. If we were to factor it, we would want to treat x sort of as a constant and factor things that way. Unfortunately, to factor this, we would need to find two numbers that multiply to equal 12 minus x and add to equal 8. And you might be able to do that for specific values of x, but not for all of them, probably. So from here, we would want to try to move to the quadratic formula. Now, moving to the quadratic formula in this case, we would have an a of 1, a b of 8, and a c of 12 minus x. So this is a bit of a weird situation where we're using the quadratic formula, but one of our terms, one of our coefficients, has a variable in it. But that's okay. We can still do this, and this will mean that y equals negative b, which is negative 8, plus or minus the square root of 8 squared minus 4 times a is 1, c is 12 minus x, all over 2 times a, which is 1. So we'll get that negative 8 plus or minus the square root of 64, and then negative 4 times this gives us minus 48, but plus 4x, all over 2. So we get y is equal to negative 8 plus or minus the square root of, let's see, 64 minus 48 is 16, plus 4x over 2. And let's go ahead and stop there a second. Because from here we can see that we are going to have a problem. In fact, we probably noticed that earlier. You probably noticed that earlier. This plus or minus here exactly suggests that we're going to have the same type of problem here as we did back when we were looking at our original problem with y squared equals 2x. Because this notation suggests that for a given x, even if we have a single x, we're going to get two different y values out of it. And that's true, that's the case. However, working through the rest of the details of this is a bit messy, not terrible, but more than we would like. And so really what would work for us is, even way back at the beginning, if we suspected that this equation didn't define y as a function of x, it would suffice to show that we've got two different y's that work for the same x. So sometimes this happens. You work through a problem and then you see, oh, wait, there's a better way of doing this than I did before. So let's solve this problem. Let's answer this question. Having gone through this process to get to the point where we're pretty sure the answer is no, this equation doesn't define y as a function of x, but now let's prove it. What we can try doing is just picking a value of x and seeing whether we get two different y values out of it. And the fact is that when an equation doesn't define y as a function of x, it's often the case that any number that you pick, or most numbers that you pick, will show you that that's the case. That if you pick just a random number for x, there'll be two different y values that satisfy the equation. The easiest number to work with is almost always 0. So let's let x be 0. If we do that, then the y value that will go with this x value will be the y value that satisfies the equation y squared plus 8y plus 12 is 0. But we can factor this. This factors as y plus 6 times y plus 2 equals 0, which means that y equals negative 6 or y equals negative 2. So that means that we got two different y values for the same x value. So that means that 0, negative 6 and 0, negative 2 both satisfy the equation, so y is not a function of x. All right, to finish up today, I've got two things to watch out for, two things to be careful of, a couple of warnings. So let's look at an example that's very similar to the one that we just did. Let's ask the question, does the equation y cubed plus 8x plus 12 equal x define y as a function of x? So the only thing I've changed here is I've changed the first power on y from a 2 to a 3. Now this equation, we can try solving for y, but we're actually going to have problems with it. Oh, I'm sorry, I made a mistake. This should be an 8y. Although actually my what I'm about to say would hold true even if that were an x, as it turns out. But for this one, we can't actually solve this for y, at least not easily. We would need some sort of cubic formula. We've got the quadratic formula for degree 2 equations. We would need a cubic formula for this one. A cubic formula exists, but it's quite complicated, and basically no one uses it except for computers. And even then, not always. And so with the tools that we have, it's usually not going to be the case that we'll be able to, by hand, solve for y here. But not being able to solve for y is not by itself enough to conclude that y is not a function of x. You need to be able to show, as we did in the past couple of examples, that there are in fact two different y's that go with a single x in order to show that y is not a function of x. In this case, as it turns out, you can't do that. In this case, the answer is yes, but it's not easy to see. In fact, the best way of seeing that this equation actually does define y as a function of x is using calculus. It turns out that if you just pick some x here, pick a particular input, there is only one y that will make this equation true, but it's not easy to see. So the point is that simply not being able to solve for y doesn't show that y isn't a function of x. You need to be able to write down equations like y equals blank or y equals blank where the two blanks are different. You need something more precise than just, I don't have the tools to solve for y. Because there are lots of equations that do define functions that you can't really solve for y on. All right, and then the second warning that I want to give is that the definition of a function says that for every input there can be only one output, but it doesn't say anything about the other way. So let's look at f of x equals x squared plus 1. This is actually the original relation x that we looked at, the original function. So this is a function where for every input x, the output is x squared plus 1. And notice that we have that f of 3 is equal to 10. We saw that last time, but let's see how that goes. It's 3 squared plus 1. 3 squared is 9, plus 1 is 10. Also, f of negative 3 is negative 3 squared plus 1, which gives us also 10, because negative 3 squared is 9, and 9 plus 1 is 10. But this, having the same output for two different inputs is perfectly fine. So a function may have the same output for two different inputs. A function may not have the same input for two different outputs, but it may have the same output for two different inputs. Just like two different items in your grocery store may have the same price with different barcodes, that's perfectly fine. But you can't have one barcode coded two different prices. That's a problem. So, the point of a function is that if you know the input that entirely predicts the output, you can figure out the output exactly. But that output might be repeated, and that's perfectly fine. It's perfectly fine for a function to have the same output for multiple inputs.